Share screen. Leave it. Well, Nope. Nope. Let's get started. Okay. I think we'll do that. Right, it's time to start. Well, hope somebody else can join us. Well, I think I've been talking to the professor, and he told me that it's going to be about 3 hours. Okay, so it's about differential equations. Differential equations and parameter curves and polar coordinates. And finally, a little bit about complex numbers. So for I think for differential equations and complex number, just some simple introduction, not too deep or complex problems. So I'd like to start with differential equations, okay? And hope you guys already know what is a differential equation. So what is a differential equation? Yes, and equation has meters and some functions about functions, right? And parameters as well. And two of them are very important in this part of the course. So the first one is something like dp over dt equals to a smaller p, right? So what's the name of this? Yes, it's something like that. Well, you know the solution for this equation? T equals to A e to the kt, right? Exactly. So based on the solution, we know that we can call this differential equation to model the exponential growth in decay, right? Okay, so we have a special name for it, exponential growth or decay. Well, they are simply the same, but they're just parameters. And we have another form of this kind of equations. It's something like this. Right? So what about this one? You know the solution for this? Or the yes, right. Right, this is called a carrying capacity. And so basically this is the reform model for this one, right? So there is a capacity that has to be considered during this model called the equation cannot flow like without any boundaries, right? So this basically is a boundary. And we call this realistic equation. Can you remember the solution for it? Or maybe we don't have to remember. So, just since we already know this chapter, may I ask you a question? Is this equation separable? The logistic equation, is it separable? How can we separate it? No. Or, they're going to write the question, how can we, determine whether a differential equation is separable? We'll go back to the topic later. So, you can write it down, this is separable. And by separable equations, we have a special treatment for it. Okay? So, as this is kind of like introduction to differential equations, we are dealing with very unique, very limited, and very simple equations. So, the first thing I want to ask is, if I give you an equation, and I give you a formula, give you a function, can you decide whether this formula is the solution to this differential equation or not? How can we decide that? So here I got a problem. Show that y equals to x minus x to the negative 1 is a solution. Is a solution to this differential equation. Y prime equals to, x times y prime plus y equals to 2x. How can we show that? I think there are multiple exercises in that book. We ask you to show that something is a solution to this equation. How can we do that?
We can take the derivative of y and then put it in as y prime to make it equal.
Right, exactly. That's how we can do it. Alright, so here we have y prime equals to 1 minus
x to the negative 2 over 2.
this is
I
x to the negative. No, we take the derivative. This is one. This is kind of like a polynomial, right? It's x to the n form. So what is the derivative? Yes. Or in a general form, x to the n, the derivative is n times x to the n minus 1. Right? So here n is negative 1. So the derivative should be negative 1 times x to the negative 2. Right? And we got y prime is 1 plus x to the negative 2. Okay, so, and we have the formula for y already, so we just plug it in to see whether the left hand side is equal to the right hand side. So we multiply x by what we just got, y prime, which is 1 plus x to the negative 2 x minus x to the negative 1, right? You simplify it, you got x plus x to the negative 1 plus x minus x to the negative 1. And this will cancel out. So we are successfully showing that this is the, y equals to x minus x to the negative 1 solution for this equation. So let's move on to the next problem. It's similar, but a little different. So the question is, for what values of r does the function y equals to e to the rt satisfies this equation? Y double prime plus y prime minus 6y equal to 0. So basically, it asks you to find out the values of r. R is right here. And to make this becomes a solution to the differential equation. And then how can we do that? Yes. So, okay, we'll do that. So what is y prime? Right. Because r times e to the rt imply the change between, right? And what about double prime? Oh, it's r squared e to the rt. Okay, so now we plug it in, we got r squared e to the rt plus r times e to the rt minus 6 e to the rt, right? Equal to 0. Here we can, so what's next? Yes, we can do that. We should factor out the e to the rt.
So then we end up getting r squared plus r minus 6 equals 0.
Yes, exactly. So we factor out e to the rt. We got r squared plus r minus 6 times e to the rt equals to 0. And we know that e to the rt is never 0, right? So this part cannot be 0. So basically we're solving for r squared plus r minus 6 equal to 0. What does it mean? Okay. We factor it? 3? How can we solve this? This is it for right? And also can we factor it? So can we factor it?
So I think it's 2.
Yes, exactly. So we can use a little factorization. We r plus 3 times r minus 2, right? Equal to 0. So the solution is r1 is negative 3, r2 is 2. These are the solutions for r, which makes this e to the rt the solution to that differential equation. Alright, so far, if, let's say for the last problem, y equals to e to the rt, well, r is not settled, or maybe we can say there are multiple r's that satisfy. We have a family of solutions of this differential equation. Well, in real life, or in modeling problem, we want that this solution to be unique. So we need some other conditions. What that is called? Yes, we have initial conditions. Initial conditions. If t is the time, or simply everything else, then when t equals 0, the y0 equals to, let us say, equals to y0, then this is the initial condition that we need to make our solution. Okay. And I don't think the book covered this kind of problem, but for differential equations, we have also some other, we may have some other condition. It's called boundary conditions. Well, you can know it for fun. I don't think it's going to be the test, but anyway, there are some differential equations that have boundary conditions. Well, let us say if the differential equation is trying to model something like a stick, and we know some property about this end and about this end, and it's kind of like a boundary. So if we know these 2 points, we can have different boundary. And for this one, I think you're going to need partial differential. Well, why we need this initial condition here? Let's just use an exercise, right? So here we're trying to verify that y equals to 1 over x plus c are solutions of y prime equals to negative y to the 2. So here we have another similar problem, which we just do. Well, this is only the first part of this problem. Oh, by the way, is there any special property for this differential equation? You know what it's called? And so that is Transer's differential equation. It really means on the right-hand side there's no t. There's no t. Right? So when we are trying to draw a direction field, if there's no t on the right-hand side, then every single, well, with the same number of y, we got the same number of derivatives. So basically, if we draw the direction field, something like this, y equals t. So for same y here, the slope are the same. Okay? Slope are the same. So it will be easier to draw the direction field, right? If there's no t on the right side. Well, let's just solve this problem for example. How can we verify that those are the solutions of y prime? Yes, it is a constant. Well, actually, from part B, we know an initial condition that y0, well, here there's no t here. Is a function, y is a function of x. So here y0 really means x equal to 0, right? So y0 equals to 0.5, we are solving for c using initial condition. So let's just focus on the first part. How to verify this is. So we have to do it all again. So what is y prime?
Negative 1 over x plus c.
Square, right? Okay. So, and we know that it's exactly negative y squared. So this is the family of solutions of this differential equation, right? Right? Okay. All right. So here, if we have the initial condition that y of 0 equals to 0.5, then can we have a unique solution here? C equals to So here, this is the value of
Just
y.
y, so we just put
Right. Right. This is plugging x equal to 0. Right? So y equals to 1 over x plus c. Well, x equal to 0 is 1 over c. Equals to 0.5. So c is 2. So this is the way that we use. So first of all, we have to know the family of solutions. That is how we solve a differential equation. First, we have something called general solution, which is something contains a constant. So basically, that's infinite many solutions. So the second step is to use the initial condition to find out which constant is actually 1. So in this case, c equals to 2, right? Okay. So let's move on to the next topic. I believe it's the direction field. And the Euler's method. Actually, there are a lot more about these two topics in further study. I think you're gonna learn it, maybe later in a course for differential equation, or maybe to a numerical. Anyway, so this is basically a geometric property of differential equation. this is the numerical way to approximate the differential equation. And the Euler's method is basically the foundation of, like, the very beginning of the numerical way to start with it. You can build on Euler's method to some further more expensive numerical algorithm. But that's something you will learn in the future. And for direction field, it's also very useful because without solving the differential equation, we can have some solve on this differential equation, like at where it goes up, right? And somewhere it goes down, and we have an equilibrium solution. Anyway, we use an example, all right? So let us sketch the direction field for this differential equation. Oh, by the way, I talked to the professor. He told me that, well, I'm obviously not sure whether there will be problems about sketching the direction field or something. But he told me that you guys should be able to draw a direction field for some differential field. Or maybe the direction field that is given, you have to use that to draw a curve of the solution using the direction field. Yes, exactly. That would be easier. And I think that's something you use in line practice because they draw the direction field freely. So for this problem, I'm not going to draw all of it, but at least some important point you have to point it out, right? So this is x, this is y. So is there any problem you notice about this difference? Yes, it's autonomous because there's no x on the right hand side, right? So basically, if here we got like maybe 0, 0, so y is 0, x has nothing to do with it, right? So if y equals 0, which is on the x axis, the slope is 1, right? So slope is always 1. What about y equals to 1? If y equals to 1, y prime is 2, so we get a little bit larger, right? Well, they are all parallel with each other because they have the same slope, right? And if y gets even larger, we get 2. So the slope is 3 again, larger and larger, right? So, well, they don't have to be very accurate, but you have to show that somehow get larger and larger, right? And what about y equals to negative 1? Well, y prime is 0. What does it mean? Yes, this is just a straight line parallel to the x-axis, right? And because y prime is equal to 0, we have that y equals to negative 1 is actually the equilibrium solution. That is how we find the equilibrium. Solution. Or we can call it equilibrium state. You'll know what it means. Well, so what if y gets smaller? Let's say y equals to negative 2. Okay, so the y prime equals to negative 1, which is like this. Right. Okay. And they're all and if you get smaller and smaller, you know that the slope will get more and more. So just for brief graph, give you a little bit idea. So while using this record field, you can generate a smoothing curve. Let's say you have, you know, if we have initial condition start here, what is the smoothing curve? No, yes, it will stay on the plot of the derivative is 0. It's not even changed. That's why it's included. So any point on this line will not change. Will not change. Right? And what about here? We just the parallel like this, right? And what about here? We just get better? Well, actually, we can solve this equation because it is a linear equation. What's the technique to solve a linear equation? This is the, I use the over the book, but for this one is 10.6, which is for the linear differential equation. First order linear differential. What is the technique? Well, if you can't remember, we'll go back to this topic. Alright? So second, we move to the Euler's method. What is the Euler's method? Anything if you can remember. Like keywords for us. Okay. Well, sure. We call that step size, right? And I think 2 is a little bit too large. Yeah. Because this is the very small, distance between two steps. Maybe we use something like 0.1 or even 0.00001, something like that. We can easily do that by the computer, but the professor told me that in this exam, they want you to know how to compute few steps about the Euler's method. Like they give you equation, they give you the step size, they want to know, maybe like the first 4 steps, what are the values of them, right? So let's just say we have an example. For this example, we use the step size h equal to 0.05. And we try to approximate values y1, y2, y3, y4. And we have the equation with the form y prime equals to y minus 2x. Here we have the first step is y of 1 equal to 0. This is given. Well, this are the 4 values they ask you to approximate. here on y1. No. Yeah. So first thing, we have to know the formula for this method, right? Okay, so it's y of n equals to yn minus 1 plus h, well, x minus 1 n yn minus 1, right? If you can remember it, just sort of things like this time, right? So what is f prime? F prime x? What is the definition of f prime? Yes. Well, what is the definition of the slope? And if we take the limit, if the limit h approaches to 0, f x plus h minus f of x over h, right? Okay. So since here we use the approximation, so we don't need this limit as well. We just use approximately the derivative, right? So here, fh by f of x plus h times fh times f prime x, right? And we know that if we call this h step size, and we have a formula for f prime x, this is exactly the order, right? This is one step forward. This is the original point, and this is the step size times the derivative. This is how I remember it. The order formula is not given. But anyway, so here we use the Order's method. Here, y of 1 equal to 0 is not necessarily mean y subscript 1 equal to 0. This is the first step. This is y of 0 equals to 0. Well, x of 0 equals to 1. That is how we interpret this here. This is the initial condition. Using that, we have y of 1 equals to y of 0 plus, well, step size is half. So half times y of 0 minus 2 times x of 0, right? Just plug in here. Right? So y of 0 is 0, well, plus 0.05 times 0 minus 2 times 1, which is negative 1. I think he's right. And by y of 2, again we apply the Order's method. Y of 2 is y of 1 plus 0.05, the step size doesn't change, times y of 1 minus 2 times x1. What is x1? x1. What is the value of x1? Exactly, it's 1.5. How do you get it? right is the one-step size after the original point, which is a x naught plus h, which is 1 plus half. So now this y of 2 is easily solved by -1, which is y of 1, plus point of y times -1 minus 2 times 1.5, which is -3. Right? By the same way, we can have y of 3 and y of 4. You can check the answer by home. Y of 3 is -6.5, while y of 4 is -12.25. You can check using a similar method. Okay. Okay. So now we move on to the separable problem. Separable equations. Again, remember when I asked you whether the logistic equation is separable or not, how can we decide that? So what is the general form for a separable equation?
The function of x.
Yes. So if we can, for a general case, y prime equals to f x y, right? Something like this. If we can separate the problem, if it is in the form of g of x times f of y, which means this is the function only with respect to x, and this is the function only contains y, then this is separable, right? And by the way, on the book, there's something called orthogonal trajectories, and mixing problems, they will not be. He told me that they will not be in the text, or just some general, like how to solve a separable equation. Well, here's the example. Well, first of all, you have to decide whether this equation is separable or not. Right? So let us say the problem is x squared plus 1 times y prime equals to x times y. It is separable. Well, we are trying to, convert this equation into the general form of a separable equation, right? So y prime here is just simply dy over dx, right? And the right hand side is x, y. So further we got it is equal to dy over dx equals to x times y over x squared plus 1. Okay? So is this separable?
No, because separated into x over x squared.
Okay, so x over x squared plus 1
Times y over x squared.
times 1. Is it the same?
I thought that you said, what is the x? Oh, sorry.
That's okay. Alright, so it is separable. Right? This is the function only with x. This is the function only with x. So it's separable. So as long as we know it's separable, we can use the technique to do the separable problem. So here we put everything only, everything about y on the one hand side. Yeah, it's dy over y equals to x over x squared plus 1 dx. Right? And we take the integral both sides. Okay, so what is the integral of this two? Okay, ln of absolute value of y. Okay, equals to so this is something. Are you very useful? Speed of two steps. Yes, exactly. It needs to be substituted. So here how can we okay, u equals x square plus y. Then du is 2x dx. Right, so we have x. So right hand side is integral of x, right? Du over u. Okay? So it is so based on natural log of u
So,
and plus c. So it is 1/2 log x squared plus 1. Actually, the actual value here is not necessary because x squared plus 1 is always positive, right? So here is this plus c. Okay, we're finished. Now we have to write something divided by right. So y is e to the or maybe we can do something like this. You remember that the 1/2 before the natural log here is this, right? So it would become the natural log of this to the 1/2, which is log square root of x square plus 1 plus c. The reason why I'm doing this is when you rise to the e, it will become much more simpler. See, is y equals to square root of x plus 1 times e to the c. Okay? Oh, e to the c is just another constant. So we can use another letter, let's just say k, right? So it's k times square root of x squared plus 1. And this is the general solution of this differential equation.
The last part.
This one here? Yeah. Okay. So this c is just a constant that can be any number, right? And here, because we raise to the power e, and so it's e to the all this stuff. So here, well, e to the 1 is itself, right? It cancels out to the square root. Here. Well, here is e to the c. Well, c is a constant, so e to the c is another constant. So we don't, I mean, if you want, you can still put an e to the c here. You understand? So this is e to the c. But that's somehow redundant because we don't need to know if it's e to the c or just simple c here, right? So we just use another letter k because there's a constant. It could be any number, right? And what about this one? du over dt equals to 2 plus 2u plus t plus tu. So now we have two parameters or two variables, u and t. First of all, is this equation separable? Is this separable? So if it is separable, we have to use we have to find some function like f of u times g of t, right? So basically here the question is, what is f of u? What is g of t? If it cannot be done, then it's not separable, otherwise it is, right? So let us say if it is separable, what is f of u? U plus 1, or 1 plus u, right? Okay. What about g of t? Okay, so 2 plus t, either way, right? How can you get it? This is correct.
You can take the 2 plus t,
Okay, 2 plus t,
and then it's 2u plus t,
right,
and then factor out.
exactly. So, let's say for is 2 plus t plus 2u plus t to the t times u, right? And here we can also factor out factor out u. Then we got 2 plus t times 1 plus u, right? So this is a function only contains t, and this is a function only contains, which means it's differential equation separable. Right? This is the g of t. This is the f of u. Okay. So as long as we know that this function is separable, sorry, the equation is separable, then can we solve it? Okay, so the function becomes du over dt equals to 2 plus t times 1 plus u. Alright? So how can we solve it? Any idea? Right. Just simply put everything, well, have u on one side and whatever only have t on the other side, right? So this becomes du over 1 plus u equals to 2 plus t dt. And we can integrate both sides. Then what we got here? This is much easier than last one. Get the log 1 plus u. Everybody got it? Everybody. Okay, so recognize 2t plus 1 half t squared plus c. Exactly, you have to put a constant at the end. And here it's not finished because we have to express u in terms of t. So we have to use the power, right? Okay, so here we got 1 plus u equals to e to the 2t plus 1 half t squared times e to the c. Well, here we do the same thing for e to the c. We just change it into another constant, namely k. Then here we have u equals to e to the 2t plus 1 half t squared. Well, we can put a k before it. Minus 1. So this is the general scheme for this differential equation. Well, it's separable. So how about just say we have the initial condition that u of 0 equals to 3. Can we solve for k? Or maybe how can we solve for k? Exactly, you just plug it in. So here u equal to 3, that t equal to 0. I mean, this is something I made up. You just find out what k is to make this equation hold. Then you use this initial condition to find u, right? Okay. Let's move on to the next. Well, next two sections are about the things I talked about at the beginning. It's basically the modeling problem for these two equations. Exponential growth with a or a logistic equation. Well, the professor told me that you don't have to remember anything about modeling. Like there won't be any problems like ask you to model from the scratch. You don't have to remember anything like for physical theorem or something. You don't need to know that. However, if a problem is asking maybe the population to be modeled by a differential equation, and they told you to use exponential growth, you have to know the equation is like this. It's for this one. well, they're going to tell you that you're going to use exponential growth, or if it's a problem using exponential decay. You have to know that you're going to use this equation and solve for it. All right, make sense? Yeah. And maybe the question is like, the problem should use the logistic equation. Then you solve for it, and plug these numbers to figure out maybe the capacity and this coefficient here. Well, I'm not sure, but that's what we told us, right? Don't have to worry about anything about modeling. Just remember how to solve this equation, and for a problem, well, I'll give you a problem. Let's make it simpler. Alright, so the problem is like this. dp over dt equals to 0.05 p minus 0.0005 p squared. Alright, so what is the carrier's capacity? No, what is the carrier? Yes, I'm just asking, like in this problem, how much is the carrying capacity? Well, maybe what model is it? Logistic equation, right? So the logistic equation is like dp over dt equals to kp times 1 minus p over k, right? You have to, convert this equation into this form and to find out what k is. So now, can you tell me how much is the carrying capacity? Is there someone who don't have this motor problem? You can do that. Oh, okay. I didn't know that. Yes, exactly, it's 100. Because if we convert this equation into this formal form, standard form, right? So it becomes 0.05p times 1 minus p over 100, right? Because this is 100, oh no, sorry, this is 100 times of the second unit. Or maybe we can, simplify this word, extend it a little bit. Here is 0.05p minus 0.05p times p over 100. So this over 100 is 0.005. That's why the complexity is 100. So let us see another. I think I'll ask you to do it by home. I think we are kind of running out of time. So, Now this problem is about cooling, right? So a cold drink. Well, it's taken from a refrigerator. Its temperature is 5 Celsius. And after 25 minutes in a room of 20 Celsius, its temperature increasing to it's increasing to 10 Celsius. Right. So the question is, what is the temperature of the drink after 50 minutes? This is part 1. The part 2 is when it will be 15 Celsius degrees. And I can let you know that you're going to use the model for exponential growth, right? You have to use the model for that. And maybe I can even give you the formula for that. Is, let's just say T is the temperature, that dT over d small t is K times the temperature minus 20. Well, 20 is the temperature for the room. So this is the difference between the temperature of drink and the temperature of room. So this is the Newton's cooling law. Well, anyway, you're going to use this model to find out. So first of all, this is the initial condition. Maybe you can transform this equation into something else, like if y is the difference between the drink temperature with the room temperature, then this equation becomes dy over dt equals to ky, which is the standard form for exponential growth. And we have, well, here 5 minus 20 is the initial condition for this equation. And you're going to use, well, after 25 minutes, it becomes 20 degrees Celsius to solve for k. And then go back to these two problems to solve for when t goes to 50 and when it will become 15 degrees Celsius. Right? I can give you the answer. That the first problem is the temperature becomes 40 over 3 degrees Celsius. And the when and the time it becomes 15 degrees Celsius is 67.74 minutes after. You can go back and do this problem and try to do it. Okay? You know how to do it now? Any idea? I mean, I don't ask you to do it now, but do you know how to do it? Sure. Okay, you can do it. Okay. So we have the original problem. The standard form is something like this, right? Instead of solving it, we're trying to convert it into another problem, which is the standard form of exponential growth, right? So here we denote y equals to t. Well, actually here we can use y of t. This is a function of t, and it changes with time, right? Y of t equals to t of t minus 20, which means the difference between the temperature of and temperature of room. So it will become dy over dt equals to ky, right? And what's the initial condition? Y naught equals to 5 minus 20, which is negative 15. And we already know the solution for this kind of equation. So y equals to a, okay, e to the at, right? And what is the a here? So a is the initial condition, right? What is the initial condition here? Okay. So by using the initial condition, we already have the exact solution here. Y is negative 15 times e to the kt, right?
Sorry, why is it negative 15?
Because we denote yt is the temperature difference. So initially, the temperature of drink is 5 degrees Celsius, while the difference is 5 minus 20, which is negative 25. Sorry, negative 15, right? Okay. So we already have this. Don't forget our condition that after 25 minutes, it becomes to 10 degrees Celsius, right? After 25 minutes, it becomes to 10 degrees Celsius. So it really means after 25 minutes, the difference becomes to 10 minus 20, which is negative 10. Right? So we plug in t equals to 25. Here we got negative 10 equals to negative 15 e to the k times 25. Right? So here we can solve for k, or we can solve for e to the k. We don't have to solve for k. We can solve for e to the k. You're going to know why we do that. Because the next question is asking us, what is the temperature after 15 minutes? Well, y of 50 is t of 50 minus 20, right? And if we plug in t equals to 50 here, well, here we have to solve for e to the k. Well, let me just tell you the answer that e to the k is 2 over 3 times 2 to the 1 over 25. Okay, by solving this, you know how to solve that, right? You just simply, verify. Alright, okay. So, y of 15, if we plug into this form, so it becomes negative 15 times e to the k. Sorry, e to the k here, we already have a number here, is 2 over 3, 2/3 over 1 over 25, right? And times 50, which is the t here. And yes, that's it. That's it, right? And this is a number. The reason why this is solved for k instead I solve for e to the k is later on we have to, use e to the k rather than k only. So we don't have to solve for k. Here we can simply use e to the k, in the whole that are just times the time t. Alright? So after doing this, you add this number to 20, you got a temperature after 15 minutes. Okay? And that will be fully over. let's move on to the final. Let's move on to the final topic of differential equation. It's the linear equation. The general form for linear equation is something like this. Our first question is linear equation separable? Yes? Good. Why? Is it separable? Or, how do you know if it is separable or not? Well, in general, it's not separable. Otherwise, we don't have to talk about it. Right? Why we spend a whole chapter or a whole section to talk about it if it is using the oriented technique and it's not separable because you see dy over dx equals to negative p of x y plus q of x. This is not a product of a function of x and a function of y. For in general, it's not. Right? So in general, it's not separable. Not separable. However, if p of x and g of x are the same, it is separable. But that's not going to be something to worry about because for a linear equation, we have a way to deal with it. Do you still remember what is called an integrating factor? Integrating factor? Well, the professor told me that he will not put integrating factor, this formula in the exam. You have to memorize it, and that you will have to use it. There will be problems that we need to. So better remember integrating factor and how to use it. Right? So if we convert the problem into the standard form, then the integrating factor is e to the integral p of x dx. And how to use this integrating factor? You just simply multiply I of x on each term before each term, and the left-hand side becomes the derivative of a product. Then you can solve it. It becomes. I'm gonna give you a. Plus 2y equals to 2e to the x. First question, is this separable? Why is not separable? When I solve a differential equation, first thing I ask myself is if it's separable. If it's separable, it's much easier to do. Otherwise, you have to use something else. So, is this separable? Why not? Okay. Because it's something like this, right? Yeah, it's not a product of function of x and function of y. Right? So it's not separable. So instead, we use the standard form of linear equation. So dy over dx minus 2y equals to 2 times e to the x. So here, let me ask you, what is p of x with respect to the standard form? What is P of x?
So the problem was what's the
Oh, the standard form is dy with dx plus P of x y equals to Q of x. So, compare this to you that Q of x here is negative 2, and Q of x is 2 times C to x. The reason why we are concerned with what is P of x is this is something in the integrating factor. So the integrating factor here is e to the integral of P of x, which is to negative 2 and dx. Oh, sorry, that is, sorry, this is a plus. This is a plus, sorry. Okay. So the integrating factor here is P of x and P is plus 2. So the integrating factor here is e to the integral 2 dx, which is e to the 2x, right? So remember what I said, we multiply each term by x. So it becomes e to the 2x times y prime, right? Plus e to the 2x times 2y equal to 2e to the x times e to the 2x, which becomes 2 times e to the 3x. And the right-hand side becomes a derivative of our product. It becomes e to the 2xy derivative equals to 2 times e to the 3x. Then what? Okay, so we integrate each side. We got the right-hand side becomes 2xy, right? It's the derivative if you take the integral, it becomes itself, right? Is integral of 2e to the 3x dx, which is
sorry.
okay. So we're going to do the rate. Okay. And okay, plus c. So we have the general solution. We can move this into the 2x on the right hand side. So y equals to 2 over 3 e to the x plus c times e to the negative 2x. You divide it by what? This is you divided by e to the 2x for the right hand side. So this is the general solution for this linear differential equation. I think we are running out of time, so I'll give you 2 examples. You can do it back home. So this is another example: xy prime plus y equal to square root of x. The solution is y equals to 2 over 3 x to the 1/2 plus C over N. You use the same method. First, it is a linear equation. You convert it into a standard form. Find the integrating factor. Multiply the integrating factor by each term. And the left-hand side becomes the derivative of a product. Then you do the integral. Finally, you find the formula for y. And this is the formula for y in this case. It's just the same routine here. But first, you have to, in an exam, they're not going to tell you it is a separable problem or linear problem. That's up to you to decide, right? You have to first say, this is a separable problem, so we do something. This is a linear problem, right? And finally, we have another example. dv over dt minus 2tb equals to 3t squared e to the t squared. And the solution for this problem is v equals to t cubed e to the t squared plus, for this one we have an initial condition that v of 0 equals to 5. And we have the unique solution is f plus 5 times e to the t squared. You can go back and check this group using the way I described it. Right? Okay, so finally we can move on to the next section. I believe it's a parametric equations and polar coordinates. Okay. So by parametric equations, just simply we use a function of t to denote x and y. And you're going to have to sketch parametric equation and maybe convert it back into the y equal to something x form. Okay. And when you sketch it, you have to put an arrow in it to show the direction. Alright, let's just do some examples. So what is the just a graph or a curve for this parametric equation? Maybe this is not really great. Maybe I just get over it. You can easily say that x times y equals to 1. And do you know the curve for this? This is called rectangular. Parabola in general is something like this. Well, this is something I think we didn't cover it, so let's forget about it. This is called the conic section. But anyway, this is called a hyperbola. And because these two are both greater than 0, so this section is not necessary, or you only need this part. So this is the curve for this parametric equation. So how about something we can deal with? X equals to sine squared theta, y equals to cosine squared theta. What is the curve for this geometric equation? So it will become no? This is that is the sum of this one because we have sine squared theta plus cosine squared theta equals to 1. And this is x. This is y. So there's x plus y equals to 1. This is 1, this is 1, so it's the 1 like this. However, you see that sine squared theta is greater or equal to 0, smaller than 1. Well, cosine squared theta is also between 0 and 1. So, in the curve, we only need this part. And don't forget, you have to put a direction arrow. So when theta is getting larger before pi over 2, sine squared theta is getting larger as well. Cosine squared theta is getting smaller, right? Okay. So you're moving this way at first. Then when you reach this point, you getting back to 0 back. You can go back and check it. The thing is, if you try to sketch a parametric equation, you have to put a direction. Yes.
So what would you put forward?
Right. So maybe you can say that this is the first. So this is the first direction, and this is the second. So because it's really not necessary, because it's going back and forth, right? It's going like this. So the only thing you need is to prove that. How about something like this? X equals to 1 plus square root of t, y equals to t squared minus 4t. Well, t is between 0 and 5. Sketch a curve for this parametric equation.
I don't think there's any isolated equation.
No, I mean, I don't think it's easier to eliminate the t in this case. So what I'm thinking is just, you know,
You find out some points like t equals to 0, t equals to 1, t equals to 2, t equals to 3, and t equals to 4, t equals to 5. Then you find out those points on the line, then connect them, right? And put a direction. So, interesting is what is the value for t equals to 0? X equals to 0. Yes. Number 1. Okay, so it's 1, 0 here, right? What about t equal to 4? Okay, x equals to 3,
and the y equals to 0. Okay.
so we have another point which is 3, 0, right? We already have 2 points, and if we want to find when t equals to 1, t equals to 2, you're gonna see there are something like here. Here. So it is something like this. And if you find the point when t equals to 5, it is 1 plus square root of 5 and 5. So it is somehow here, you say, right? So you connect them, so the curve becomes this. And you see as TE increasing, the curve is moving the way arrow is moving. That's how you sketch something that you can't eliminate T. You have to sketch it by using some point and be equal to some sign.
The next thing is calculus for parametric equation, which means you have to find the slope at some certain points, the area between some curve, and the arc length. And in the exam, there will be no surface area. Do you still remember the formula for derivative?
In this case, let us say x equals to f of t, y equals to g. Then what is dy over dx? Yes.
So it becomes g prime t over f prime t. What about maybe the second order derivative? Is it g double prime t over f double prime t? Yeah? No, it's not. It's not. You're gonna see this is d over dt. Sorry. D over dx g prime t over f prime t. And here we can take derivative with respect to x. So it becomes dt over dx over dt. And you'll see they are not the same. So you can use the double prime. Just remember, you can't use it. You can't. They're not the same. Just using this formula once again. you take the derivative with respect to t, and divided by x prime. In this case, I think it's f. Okay. This is over f prime t. Okay. So this is the first order derivative. And this is the function of t. So when you take another order derivative, this really means this over dt over dx, which is f prime t. Okay? Very good. So let's just do some exercise. So find the tangent to the curve at the point. We have the equation is x equal to e to the square root of t and y equal to t minus ln t squared. Well, we want to find the tangent line at point when t equals to 1. So we want to find that tangent line. Since we are running out of time, I can tell you something in advance. As for color coordinates, right? So here we use x equal to f of t, y equal to g of t. But for polar coordinates, it's really transforming to x equal to r cosine theta, y equal to r sine theta, right? And the polar coordinates is r theta, right? And somehow we're gonna do the same thing for the polar coordinates as well. The same thing, sketch, find the derivative, and the area, and the arc length. The same thing, all of them. It's just something, well, different, but we use the same principle. Right? So here for this one, find the tangent line in this curve. This is a trigonometric equation. I guess I spent too much time on this. If we want to know the formula for this tangent line, we need two methods. One is the Cartesian coordinates for this point, x and y, and the slope, which is dy over dx. Then we can find the tangent line, right? So what is the Cartesian coordinates at this point when t equals to 1? Is okay, so what is x equals to okay, so e to the first is so e. What about y? Here's t squared, ln natural log t squared, which is
log 1 0. So y equals to 4. Okay. So the Cartesian coordinates is E1. Okay. And what about the slope?
Y over dx. Remember what we just got is g prime t over f prime t, right? What is g prime t here? Okay, so it's y prime, right? What is the derivative of y? 1 minus 1 over t squared times 2t, right? This is the change rule. Over e to the square root of t times 1/2 times 1 over square root of t. Right? Again, it's change rule. This, if you take this as u, so it becomes e to the u times u prime. Right? And the derivative of the square root of t becomes 1/2 times t to the negative 1/2. Right? Well, anyway, we only need the value when t equals to 1. So we just plug it in. You don't have to simplify. So here, when t equals to 1, it becomes 2, right? So it becomes 1 minus 2. What about the denominator? 1 over 2 times e, right? So it really equals to, negative 2 over e, right? So we have that this point is E1. Well, the slope is negative 2 over e. So the formula for the line is simply y minus y equals to negative 2 over e times x minus e. Okay? So simplify it, we got y equals to negative 2 over ex plus 3. Okay. The next problem is find the curve's length. The arc length, the length of x equals to 1 plus 3t squared, y equals to 4 plus 2t squared, while t is between 0 and 1. What is the arc length of this curve? Okay, the integral. What are the bounds? 0 to 1, okay. Square root of square root of square plus okay. dx over dt square. Y over dt squared dt. Okay. I mean, I kind of forget who told me about it. I think you don't have to remember it, but you just got to know how to use it, right? Well, anyway, there's going to be a reading session from your professor tomorrow or okay, so whatever you do.
but it's not a hard number. It's just square root of square. So in this case, is the integral from 0 to 1 of square root. So what is in here? 6t squared, right? Plus this is cube. So 6t squared, right? 36 t to the 4th, right? And dt. So now the problem is how do we deal with this?
Can you factor out 36?
Yes, we can do that. So it's square root of 36t squared plus 36t to the 4th, right? dt. So it becomes the integral of the square root of 36t squared, we calculate out, becomes 1 plus t squared dt, right? And don't forget, this is also a square, so after the square root, it becomes 6t times square root of 1 plus t squared dt. We can do that. Oops. So it's going like t, right? This is 6. Right? Okay. Any technique here? So we are running out of time. I'm just going to tell you that we use substitution that u equals to 1 plus t squared. Okay? So du equals to 2t dt. So t times dt is really 1/2 du. So it becomes 6. Don't forget to change the bound. Okay? When t is from 0 to 1, u is from 1 to 2. Okay? And this becomes square root of u times 1/2 du. Then it is solvable. Well, I'm just going to tell the answer. It's 4 times square root of 2 minus 2. Alright, we don't have any time left, so so here's another problem. I want you to find the area between this symmetric equation. When theta is from between 0 and 2 pi. First, you have to sketch it to see how this curve goes. and Boolean row. Right? So by the area is GT F prime T dt. Right? Well, here is not necessarily T, it's actually theta. But anyway. And for this problem, the answer is I and B. Well, actually, it is this. This is -1, maybe this is A, this is B, this is -B, the curve is like this. Well, this is not a circle. So just talk a little bit about complex number. Complex number. So something like A plus BI, right? This is called the real part. This is the complex part. So for real number, B equal to 0, right? And we have to find the complex conjugate, which is A minus BI, right? And let's do one problem. Okay, so what is I cubed? Yes, it's negative. Okay. So what about this? 1 plus 4i over 3 plus 2i. How do we do this? Exactly. So 3 minus 2i over 3 minus 2i, right? So it becomes, what about a numerator? Three plus 12i, right? Minus 2i minus 8i squared over 9 minus 4i squared. Okay? And we combine them. This becomes plus 8, right? So it becomes 11 plus 10i over 9 plus 4 is 13, right? So it becomes 11 over 13 plus 10 over 13. That's another complex number. Right? And there's the polar coordinates for complex number. It is simply A equals to R cosine theta, B is R sine theta, where R is square root of A squared plus B squared, which is called the absolute value or modulus of complex number. Okay. And you have to know how to convert, a complex number in A plus BI form into the polar coordinates. Okay, that's it. I hope you, Professor, did another review session. I hope it's helpful.
Thank you.
No problem.
Have a good night.
You too. Thank you.